Yeah, thank you, Alain. So yes, I'm going to present this joint work with Yazid that is here. And Yazid, if you want to complement anything on the presentation, do not hesitate. It's really nice presenting this work here because actually most of it was done during our stay at INI 4 weeks ago. So, so it's it's pretty nice. So yeah, I'm a PhD student with Eric. Yazid is finishing his PhD with Sylvain, and we were working on this together. But before starting the main part of the paper, I'd like to talk about one linear inverse problem that I'm really interested in, because my PhD is joined with the Lyric Institute, which is a cardiology laboratory in Bordeaux, France, that wants to work on sudden death, on stratification of sudden death. And something that is kind of the ideal way of tackling this is by doing ECGI. So ECGI is the ECG inverse problem, also called ECG imaging. So the whole idea is that you're going to observe potentials, electric potentials on the surface of on the torso. So this is the surface. And what you want to do is reconstruct the electric potential at the epicardium. So the outer part of the heart. In most cases, you know the transmission. For example, if you do MRI and tomography, you can kind of estimate what is the propagation matrix from the epicardium to the surface. Of course, this problem is really imposed, but it's linear. And people have been trying to do this, for example, by using Tikhonov regularization and a lot of different methods. Right now, the belief in the field is that this should not be done. You should do machine learning. You should try to learn directly because you have collected a huge amount of data, but it's hard collecting a huge amount of data. And I think that we can try with this kind of deep generative priors to solve this problem, because maybe collecting data of epicardial potentials is easier. You can just run a lot of simulations. Well, it's not easy to collect real data, but you have a lot of different computer models, and you can use a generative model trained on this, like as a prior. I would love to do this kind of hard, running a lot of simulation with a lot of different heart shapes. But I just wanted to present this as a different kind of application that we can have, because we have a lot of interesting things. I learned a lot of different stuff here. And so I say maybe I should give some feedback and show a kind of different application. So mainly that's it. We can talk more about it later if you want. So let's start with the presentation. So we are interested in a Bayesian linear inverse problem. So I think we saw you guys saw this several times. So you have your measurement equation that is linear. You have some additive Gaussian noise with some standard deviation, and we suppose that our data distribution of X is our prior is a generative is a score-based generative model. So that is what within diffusion based, but yeah, you guys know what I'm talking about. For this talk, I'm going to kind of use the reduced version of this problem, the simplified version. So I'm just considering that my measurement equation is this one here, where you have a diagonal matrix and you're only observing a certain part of the space. So if you kind of dividing your space into the observed coordinates and the non-observed coordinates. So y is a measurement of the observed coordinates rescaled. Then you have your additive noise. And our goal is to draw approximate samples from two posteriors. So I'm dividing this in kind of two different problems. We're going to see that you can actually use one of the problems to solve the second one. So the first problem is what is called the noiseless problem, which is you can also call it in painting. So you are perfectly observing the observed part, and you have the bottom part. Then I'm going to be calling this top and bottom for the rest of the talk. So the top is the observed part, and the bottom is the non-observed part. And then you have also your noisy setting where you don't have a delta, a Dirac, you have this potential that comes from your measurement equation. So, and the goal, of course, is to do this without, well, at least our goal is to do this without having any additional learning. We do not want to optimize anything to sample from those posteriors. So this is kind of our task. That's our goal here. So I know you guys have seen a lot of diffusion, of ways of presenting the diffusion. I think this one can be a little bit different. It's kind of like the version that Alain presented called variational inference in his talk, but let's just go through it so I can also fix the notation. So you have the forward process. I'm going to use I always have trouble with this name, but the autoregressive one. So you guys have seen this several times. You have this Markovian forward process. I'm going to be using, so MS is your transition. You know your marginals conditional on x0. Have an expression for it, and I'm going to write the marginals as this kind of strange n. But what is important here is actually I'm going to be following the DDIM paper, which actually relies on something a little bit different, which resembles is the inference process. So what is the inference process? This is what, for example, in DDPM is called the bridge. But here we're going to talk about inference inference process. So you have this non-Markovian process that is defined here. So you know the probability of xs minus 1 conditional xs x0. You start with the same. You have your final distribution that is the same distribution as the forward process that from DDPM, for example, and you're gonna come back with this given formula. Why we're choosing this mean function? We chose this mean function because, as Song showed in his paper, the DDE paper, when you chose this function for no matter what choice of sigma s, if sigma s is in this given interval, you actually have the marginals that match. Okay, so basically that's what's important for us, the inference process. And the thing that is interesting is that it matches the kind of forward process that is normally used for the DPM. And our goal now is to approximate this inference process by a Markovian backward process. And how do we define it? To define it, we first start with what we called here several times the kind of prediction of x0 from xs. So this is somehow you're reversing the marginal distribution here. This one, you're kind of trying to reverse it with your epsilon network. And what you're gonna do is, if you have this prediction of x0 from xs, what you're gonna do is gonna define a variational family that is basically you're gonna plug this prediction over your x0 from your inference process. Okay. It's okay for if anybody has any questions, you hesitate to ask. So you're gonna do this. And what you're gonna do in the last step, of course, you cannot do this. You're just gonna predict from x1, x0, and you're gonna add some variance. This is the free parameter. And if you want to minimize the KL divergence between this variational family and your inference process, what you get is this loss, that is the denoising loss. So what you're trying to do is that you get some data, you sample some data, you sample some noise, you're gonna do the corruption according to your marginal, to your marginal, and you're gonna try to predict the noise. So this is something that we are everybody knows this, and what they exploit in DDAM actually is that if you have a minimizer for this problem, you can actually rescale sigma s, because if you just change the scale of sigma s everywhere for every s, you have the same optimization problem. So this is what they do, and this is kind of the main point of their paper, that you can, if you have learned this model, you can then rescale and have less noise, and then you can have some nice things if you downsample the number of steps you're doing, if you skip some steps. So this is the basic idea. So this is the diffusion model. I'm sorry I presented it for this 10th time this week, but yeah, it was kind of important for the notations. So here I'm going to show what happens in the diffusion. So here we're doing this backward diffusion thing. It's not working. Yeah. So I have, this is my data. So it's a mixture of Gaussian, I think in dimension 800, but you have the same pattern in every 2D dimensions. If you want more details about it, we can talk in the end. And of course, it's not uniform Gaussian. You have different weights that are drawn. And you see the diffusion, you're getting, the colors are a bit softer, I don't know if you guys are seeing, but then you get your diffusion. Basically, you run this back. And this is a case, of course, where the score is known, as, for example, we talked a lot about here. So we know the score, you can just run this backward thing, and you get back to your distribution. So this is something that everybody knows. So let's talk about how we're going to try to solve this now. So basically, let's focus first on the noiseless case or the impending case. So the target posterior, if we write the full backward distribution, you have this decomposition, and the target posterior is the zero marginal of it. You can see that, and everybody knows this, that it's not a good idea to try to do some Monte Carlo stuff to approximate it. So how can we do it? One idea is to try to guide the backward process. So this is kind of a really basic idea. We're gonna try to find some potential G and write this sequence of distribution that is going to slowly converge to phi0. So this is our framework. Of course, when you do this when you add this kind of function, you have some bias. So a way to solve this problem and really get to phi0 is by doing the following recursion. So you're going to start. You have one approximation. You're gonna propagate through the backward kernel, and you're gonna reweight by this ratio of your guiding functions. Guiding function at time s, and divided by the guide function at time s plus 1. Sorry. In the end, to get the posterior, you just divide it by g1, and you propagate according to the backward kernel from 1 to 0. Okay, so this is basically the idea. Of course, our goal is to find G that's going to make this thing work. So it's going to guide the backward distribution, and at the same time having this kind of property of getting this distribution to be closed as we had in the purely backward propagation.
So just as an addition, the PS t-axis, that's the marginal of the diffusion model at time s, right?
Yes, the backward.
The backward at time s.
Yes, the backward kernel. So this is our approximation at time s plus 1, and this is the backward kernel from s plus 1 to s. This is your guiding function for at time s, and you divide it by what you weighted this distribution. Okay, so you can cancel this. Wait, thank you. Yeah. So here I said basically not much. I'm just saying the general framework. So how do we solve this kind of things? We propose to use sequential Monte Carlo approximation. So we talked about this already on the morning. So the idea is that you're going to approximate each of your TS by an empirical distribution. So a sum of, you're going to use particles to approximate it basically. So suppose we have this empirical distribution at iteration at s plus 1. If we plug it into the recursion, we're gonna, and here is kind of the main idea of our paper, is that how are we going to pass from TS plus 1 to TS is that we are going to use an auxiliary kernel and weight function that are defined as such. So here we are making a kind of, we are assuming that we can have this conjugation here. So we can explicitly calculate what is this transition. So we have a closed, we know how to sample from this PSY, and we're gonna sample it and use this weight function. This weight function is of course imposed by the fact that we want to sample from this.
So this is still the weight, I mean, the noiseless, I mean, no measurement errors.
No measurement errors, yeah.
Then everything is general. I mean, how do you do this?
At 0 is degenerate, but when you go forward, you already adding noise. At 0, we have to do something particular, yeah. So this is for every S except 0, and I'll do a special part for 0. We have a different weight, and you have a different.
Generally, it's actually get closer and closer, right? I mean,
yeah.
I can see that the further away, yes, you can do what you want. But,
as you get close, it's going to degenerate, yeah. And basically, as you get close, you're going to see it the less iteration. Just yeah. So if we plug this with these approximations on the recursion, we get this mixture model. And of course, to sample from this mixture model, what you do is you sample a categorical variable, your ancestor according to the self-normalized weights, and you're gonna propagate according to the kernel supported condition on this ancestor particle. This is standard sequential Monte Carlo. And so, as I was saying, for the last iterations, you do things a little bit different. So the last iteration, of course, we're not using an auxiliary kernel. What we're doing is basically a bootstrap step. So we are propagating according to the backward kernel from X1, and we are putting a direct on the top. So the observed part we put in the measurement, and the bottom is just weighted by these weights that correspond to the bootstrap step.
How do you hit the Dirac delta with samples?
So we impose the direct delta, and then we how do you say, you glue the bottom part. So basically what you want to do is really
okay, so because you independent.
Yeah.
Why don't you do this right from the beginning, right?
What? Yeah, I could. So this is SMCD basically. What they do is that they forward the measurements, the top part of the measurement, because the forward process is independent, like coordinate-wise independent, and then you're gonna use this and just draw the bottom part of it, right? The problem with this is that if you actually,
I mean,
how would you?
You're introducing some bias.
yeah, you do, right? I mean,
Yeah,
but also in the last step, you introduce some bias. If you do it like here, right? Maybe you put enough already, but that last step is also doing something, right?
But you're just replacing the top zero with the y.
Yeah,
Yeah, but I mean, also that is also a projection step. I mean, maybe everything is already close enough, but that doesn't. It would be worse if you were to do it right in the beginning, but
What you're hoping for is the bottom, when you're close to zero, the bottom is already matching the y.
yeah.
When you
yes.
If you choose-
but still, I mean, it's, the last thing is you then just say, okay, now I throw it away, right? Basically.
Yeah, that's yeah. That's the whole idea of guiding it. But actually, so the SMCD.
But I mean, again, I mean, this is the question. I mean, your sequential Monte Carlo method becomes very inefficient as you get closer and closer to whatever the 0 or n. I mean,
Yeah.
whatever when you want to hit the distribution, right? So then, because it gets more and more, the G will become more and more general too, right? Because trying to really pull stuff in now.
It of course depends on your choice of G. If you could have like this perfect choice of G, you could guide it really smoothly. But yeah, if you have a good choice of G and the problem is easy enough, it's not going to be degenerate. If you have a bad one and the problem is hard, we're going to see.
You haven't told us yet how you find the G's, right?
Yeah, exactly. We're going to talk about this right now. So because we talked about it, no, I'll talk about SMCD later. Let's talk about it later. I think no, it's better idea. So
And
then
the
choice of
sequential-
potentials. So
Sorry, in the sequential Monte Carlo, where do you get the samples from? I mean, you start, let's say, from the Gaussian.
Yeah.
And then you just decide on a number of how many you choose.
yeah, so you have a number of particles. And then, so this is the big N here.
But that's much smaller than the number of samples you have that generates your prior, the data points that generate your prior.
Your data set from training data set.
Yeah.
Yeah, it can be. It's not that smaller enough. It depends of the, yeah, but it's probably, I mean, I can do 100,000 particles. So I can have N equals 100,000 and it's going to run under 20 minutes, but
Okay.
yeah, but it depends of your data set, of course. So here, the idea is so how can we choose the potentials? So this is kind of, we can actually bound the KL distance between the real posterior and the expectancy over the empirical measure that we get from our SMC sampler. And we can actually bound this by this, you have this O(n) square term, and then you have this O of n term, and you have this expression for C for the constant. So this expression, in the beginning, we were kind of trying to see what we can do of it, but it actually suggests what would be the ideal potential. And the ideal potential is actually taking GS of y equals this. If you take it equals exactly this, you're gonna have 1. This is going to simplify to 1, and you have a bound that is small n. Small n is the number of steps of the diffusion over n. Okay.
What is below Z here? The Z of S
Is your
some of the measure.
yeah, you have your S Y.
It's improved the.
So it's your margin of your SMC, the log of your recursion at time S.
It's improved the bottom and top part.
Yeah, we defined it everywhere.
Okay, also so that.
For the moment, I haven't defined my G, so for the moment, my G takes the whole space.
I
But
think there's just a small mistake in the notation. So G depends also on the, I mean, it could depend on the whole vector. So if it's not,
yeah.
it's not the.
Yeah, G depends on the whole vector. Yeah, I'm sorry. Yeah, exactly. Yeah, I have to fix this. Yeah, thank you. But yes, so
But basically, you're trying to solve, I mean, SMC is called the optimal proposal. You're
yeah,
trying to find the optimal proposal
exactly.
with a singular target. I haven't seen that. I mean, that this can be done in a meaningful way.
Well, a spoiler is that we're not going to use really this, but this is just going to kind of motivate it because we cannot really compute this because this basically what's saying is that you're looking for the transition from your step ZS to X0 and you're kind of calculating this. But so this is sensible, but it's
well understood theory how in principle it should be doing it, right? So you have an underlying diffusion process. You have a change of measure at the final time. And if you optimally want to guide it, it's optimal. I mean, it's an optimal proposal or control, whatever you want to call it.
yeah. Okay, yeah. So exactly that's what I just said. That we have this potential. This is this optimal choice. You have the importance weight is going to be 1 over n. So you know this is your optimal proposal, but it's an intractable proposal. So we cannot really do this. But so what we are doing is that at least our first go at it that was done here is to kind of try to interpret it as basically you want to know what are the states at time ZS that's going to give you y at time 0, and the poor thing to do, like this, the thing that is more economical to do in the beginning is just set it as the forward of your measurements. So you can take your measurements and you can put it forward through your forward diffusion or your inference process. You know that the inference process has the same marginal as the forward diffusion. So, and it's coordinate-wise independent. So basically, this is our GS of y. So we know that this is larger than the optimal proposal. But we know that if you have some xs that is going to generate a good y, it should be probable in this distribution. And the good thing with it, and that's kind of the most important thing for us, because we tested doing bootstrap methods, is that this you can conjugate it with the backward kernel, and you have this kind of Kalman filter like step and weights. And everything is tractable. And the good thing here is that you're gonna, by doing this, using this proposal, you're conjugating both the backward and the guiding function. So this is something that we saw that was way better than just doing bootstrap and things like this.
So if you think of continuous time, you would have your diffusion process, and then you would add the Kalman term like that pulls the particles
towards what the forward,
the observations.
Yeah.
In an increasingly forceful way.
Exactly. Yeah, that's it. And the thing is that I think maybe so. Yeah, here you have exactly the kind of Kalman update interpretation. You have the Kalman gain that is here, and you have you're doing this kind of weighted mean between your observation and the mean from the big bridge. And the good thing here is that we are nonlinear on S+1, but we with respect to.
And the gain is scalar there. Oh, because you have sort of, no, wait a minute. This KS down there. The
Yeah.
footnote is a scalar coefficient for each of the observed, observed components.
Yes, because you have this.
For each S.
Yeah, but only the observed things. right?
Only on the observed things. Yeah.
Okay, that's a further simplification. So it's not really Kalman, it's sort of nudging. I would call it nudging.
Nudging.
Well, this is not statistically justified, right? I mean, you're just doing some nudging, yes, not Kalman. I would call it Kalman.
Yeah, no, yeah, just saying
Python
that.
has a very specific gain, which is really motivated by, the uncertainty, etc.
But you. Okay, I don't really, but this really writes like the update part of your Kalman distribution, because you have like this linear Gaussian measurement model, and you have your prior, as you say in Kalman.
Whereas the prior,
So this is a,
sigma S is,
so basically if I go back, you have it here. So this is a Gaussian kernel. Like Gaussian kernel is not really well defined, but this is a Gaussian kernel with fixed variance, with a mean that is non-linear of x(1), and then you have this Gaussian potential. So you can
not depending on the kernel, it depends on the uncertainty in XS, I suppose. Not on the model error or something.
So this
I mean, the Kalman, in Kalman, you have a prediction step, that would be your transition kernel, and then you look at the distribution in XS.
Yeah.
And then you have a likelihood, and then you do based on that uncertainty in XS, not the model error.
Yes.
Not the error that you introduced in the prediction step, and then that goes into Kalman. But you using, if I understand correctly, now you're using the error that comes through the model.
No, this
Sigma S is the model error. Right?
no, it's not the model error. Sigma S.
What is the sigma S?
Sigma S is is from the infront, from the backward kernel, basically. It's the variance of the backward kernel.
Yeah, that's the model error.
Yeah.
Anyway, I think that it's not Kalman.
Okay, I'm interested in continuing this afterwards. So we said this, then we have this proposal, we have everything is analytical, and I think, so yeah, just this is connected to a lot of stuff. This is connected to a lot of stuff that exists, but it's different at the same time. So SMC diff is basically drawing from this distribution and imposing that your top is according to this. And you impose it, and then you draw just the bottom. So this is justified if the joint laws of your forward and backward distributions are exactly the same. This is their results are proved on this case. For us, we do not need this to be true to prove our bound on the KL. So this is one of the difference. And then actually there is algorithm that's pretty well known. We talked about it this morning. That is the DPS. Exactly the DPS algorithm. That's basically going to try to target the score of the posterior. So basically, you say the score of the posterior. So here it's not everything not properly defined, but you can think of the posterior, the forward conditional model. So the forward conditional model is XS given Y, and you're going to write this the gradient of the log as the score that you had for your prior plus this term, and this term really resembles a lot the term that it's kind of the optimal term. And then the approximation that they do to be able to calculate this is that they say basically that the gradient of the log of this thing is just the gradient of log of the potential using the prediction. From XS, you try to predict it 0, and you look at the potential and do it. So this is kind of the questions. So this is basically DPS. And then, so here we're gonna see that, so here we're gonna compare ourselves and DPS. So this is MCGD. So this is our prior, it's a new, it's the same one as the previous as I showed previously, but just I redraw the weights. So the weights are draw different, the weights of each component. I draw a linear measurement model. So I draw a matrix randomly, I draw some noise, and then I draw an observation Y. And then, of course, it's a mixture of Gaussian models, so you know exactly the posterior, so you can sample from the posterior, you can do whatever you want. And then we make, oh, sorry. And we can run both algorithms. Sorry. Yeah. So here we are seeing basically what we're seeing is the evolution of TS. Why? In the beginning, we kind of have this similar. And then you can see that DPS is gonna overshoot it to the posterior distribution, while ours is kind of, oh, sorry. Yeah, you're gonna see that we go. Huh? No, well, measurement dimension is 1, and the space dimension is 800, I think. I'm just showing the true first part of it, but yeah. Well, it's dimensional, it's low dimension, yeah. But the thing here is that we can, so basically the thing here is that we can actually calculate everything. So we can actually have some compared to the real posterior. So basically that's our goal in this paper. So before I go into more numerical results in this case, I'm just going to talk a little bit about the extension to the noisy case. Okay. So in the noisy case, our posterior is written like this. What is important is that we are in a setting where the observations are coordinate-wise independent. So here the likelihood can be written as the product for each of the coordinates of the observed vector y, and we assume that for each coordinate there is what we call a meeting time. There is a moment where the measurement noise divided by the diagonal value of this coordinate is equal to this quantity that depends on the coefficient of the Ford diffusion. And over this total time, this meeting time y, what we have is that we can rewrite the potential. If we go from the normal, for the definition of the Gaussian, where epsilon is a Gaussian 0, 1 noise, and we multiply both sides by this quantity, what we have is that this quantity follows the forward margin. So this quantity is actually is a marginal from M to Y. So basically what we're saying is that this quantity here is a realization of one of the marginals of the forward diffusion. So this is a way of saying that actually what we can do is solve impinging problem between tau y and t, and small m in our presentation. So basically we're gonna, use everything, use the guiding functions that we had previously, but we're gonna start from tau y, and we're gonna say that this is an observation of tau y and tau y. So our potential here, so here for we're not going to impose a hard constraint on delta, so we are approximating the delta by some small variance Gaussian, and then our potentials, these are the potentials from the forward, the same potentials that we used before, but from tau y until t for each coordinate. And then what we can see, I'm going to skip that, I think. What we can see is that this seems to work pretty well in the mixture of Gaussian case. So here I augmented the dimension of my observations to 4. And what I'm looking is the evolution of each of the coordinates, each of the observed coordinates. So the blue dot is the blue dot that I'm imposing. So from between, for example, this blue dot and here, I have potential G's that are guiding this toward this. The blue curve is the mean of my G function. And from here on, I'm not filtering this anymore. I'm not guiding this part here. Because basically what I said, if I impose here, and if I just run the denoiser, so the diffusion backward is going to denoise it. And this seems to actually be the case. And we can actually prove here if you assume that forward and backward are exactly the same, the joint is the same, you can actually prove that you can write your posterior as the same posterior as before, but with directs at the times tau e. So this is, of course, we're not really we don't need this assumption for our SLC method to work. But if this is true, we can actually prove that this this idea of saying that the noisy Gaussian problem is actually a succession of noiseless problems, but not starting at 0 but starting at tau e for each coordinate. And then, we have this kind of more interesting result. So basically, what we did is that we generated several different different linear measurement systems, and we calculated the Slicer-Wallerstein between our true posterior and the samples that we obtained from each of the algorithms. So this table here is 20 steps of the DEM. This table here is 100 steps of the DEM. So basically, you can see, we see that we have smaller Slicer-Wallerstein for all the cases. For when you have more steps of the DEM, then GPS becomes quite competitive. It's still worse than us, but then there's a lot of overlap of the confidence intervals. But we're still kind of better in more ill-posed parts. So the ill-posed is like when the dimension of the observation, dy, is way smaller than the dimension of the space. And so this is kind of something that is the first step for us. We are actually working on, can we use something more related to DPS as our guiding function, combining the two? Then we have tried our algorithm on a higher dimensional data set. So this is Celeb HD with 256 pixels by 256, I think. Yeah, that's it. And we are focusing on, of course, in more well-posed problems, everything works. And then we focus on really ill-posed problems. And what we see is that in these cases, we can see that we have seem to have some diversity. Of course, as you said, there are some problems when you glue things together. We can see that you can actually kind of see the square. But
it doesn't seem to be the case for CGS. And it seems like, I don't know, it seems to be more better at
the gluing part, is that because as you use your kind of what you do is that you're kind of using the bottom part to try to denoise the top part when you.
Oh yeah, you're never using that in the.
Yeah, we're never using that. So this is something that we kind of want to do. So how can you use the bottom part to correlate more with the top part? Because for us it's kind of independent. But the thing is that we did not want to put some non-linear thing, so we cannot conjugate and have this kind of auxiliary kernel that's guiding a lot. So we're kind of currently trying to do this and maybe using the kind of DPS thing as a weighting, but we kind of.
So the problem is if you use the same condition as DPS, they take in the gradient with respect to the score. Yeah. And if you have a 1,000 particle, you have to take the gradient.
Yeah.
It's quite expensive. So if you use other kernels that do not take the gradient, you can use much more particles than.
Yeah, it's
this sort of constraint.
And actually, what you can also see is that maybe trying to denoise the top part is not, well, it's something that you want, but you still want to be in a place of high density of your marginals. And sometimes doing this, you can actually see that if your things are independent, then you can kind of get out of the marginal density, and then you can, if you really push it a lot, and you really say, I really want to optimize my bottom to really denoise the top part. With some networks, you can see this kind of adversarial attack where the bottom part is going to have some strange features, but then we're going to noise really well the top part. So it's kind of, I think it's a balancing act a little bit this, and we hope we're gonna find the answer really soon, but I don't know it yet. So here, just something that I wanted to show is the kind of evolution of the particle cloud. So you see here on the top, the numbers indicate the S, so the iteration. You go from 1000 to 0. And what I'm showing is the prediction of X0 on this one. And you can see kind of what happens. I kind of like this image. I don't know why, but most of the papers, when they try to do this, the first image is green. So just something that Celeb seems to be doing that. So you can see this in a lot of different papers. And actually, I think that's all. Sorry.
But you're using some sort of sequential Monte Carlo of this.
Yeah. So this
So
is
you actually have in each of the iteration index, you have many images.
yeah, exactly.
And they all look the same in the end, or what is the?
This is a
Or
good
you're just
question.
showing us one here,
I'm just showing one. Yeah.
and what do the other ones?
Most of the time it does collapse in the end. Yeah. You kind of
In between, I mean. you
in
should
between
see
it
a lot
actually
of choice.
yeah, you can actually see a lot of choice up until I would say something like here. And then you kind of when as you are the problem is that your weight is
In
gonna
a way, it should quantify the uncertainty, right? So if
Yeah.
you just have a little snapshot you show, and there are actually many faces that fit that. Especially if it comes to models, they all look the same essentially.
yeah, I think we can do
Then you should see a lot of models, right?
Yeah. But this is yeah.
And well, also in the end, right? It should not collapse. I mean,
Yeah.
well, they all show one image. Yeah.
No, wait. Several images for MCG. Put this in the top.
Oh,
So you have said already.
that's your method. Or is
Yeah, MCGT is our method. Yeah, this is our method.
SMC is not.
It's not our method yet. So it's basically the thing where you fix your top during the whole backward draw.
And that makes it unique, or would you also have different images?
No, they can also have different images.
Okay.
From one run or from 4 different runs of the algorithm?
So yeah, so basically here we have I think these two are from the same run. And but yeah, it's 2 runs here, I think. And the thing is that effectively you get some diversity, but you 256 is pretty huge. So when you're calculating weights, you're calculating basically L2 distance between 200 huge spaces. So when you self-normalize, your weights kind of have like this kind of 1 or 0 thing. So this is kind of the problem. And there are a lot of things that maybe we can do to try to bring this dimension
So you
down.
have a weight collapse still, right?
Yeah. Yeah, weight does collapse.
So you don't care here, right?
We
Well, I
can.
mean, you want to have one image, right?
How many particles
So
do you
it's-
have?
So here is 10,000. Yeah, but the thing like yeah. Problem.
So then it collapses into one.
This is also a trade-off. I mean, if you so you're something from if you're in low dimension, you're something from the right posterior compared to the other methods. But then the trade-off is in large dimension.
We all know that that's in, these methods basically.
Yeah, yeah, exactly. We knew that. We kind of wanted to test ourselves in Celeb just to see what happened. But yeah, we knew that particle filters and sequential Monte Carlo.
Collapses into a model.
Yeah, exactly. So yeah, that's it. Yeah, that's it. So thank you. If you have questions.
We don't try. We don't try and do ECGI.
No, not yet. Yeah, I want to have a score-based model of epicardium, but I can't find a database. So if you guys have one, I do accept it. So I'm thinking about trying to learn to do some modeling to generate myself with iconal models or stuff like this. So this is something that can be interesting. But I'm actually also working in trying to find the diffusion model for the ECG, or actually directly modeling ECG and some stuff. So yeah. But if you
could start by simplifying.
But yeah, iconal. But then the problem is that you lose kind of the linear thing with iconal, right?
Yeah.
Yeah.
Sure.
Yeah, you're not non-linear, and then but you know the operator, so yeah.
So why don't you just model use polyvar?
Well, actually, no, polyvar. Here, like they don't have the for the Institut branch, they don't have the forward model.
But you have the yeah. It depends.
You trained before, right? I mean, you fix
No,
your.
yeah, when you write it as the Bayesian inverse polytechnique, they don't like they don't know how let's say the propagation on the path.
But if, I mean, you first train your general score generative model.
Yeah.
At that point, you have an SE model that transforms the Gaussian to the whole image set. I mean, like to your
Picardian potentials, you're right.
yeah.
And then you propagate to the torso.
Right, and then
What I say is that it's just most of the case, but they do is a variational without the forward model. Because basically they use each time step as a different representation of what is going on there.
Yeah, I think
without knowing that from one time step to the other, basically what is going on and the Picardian changing to
yeah.
it's 41.
Yeah,
You know, you have the model, and then in the end, you have your like you have you just compose it, you write it down, and you do your map estimator that gives you a beautiful image.
but it's imposed anyway, so why not?
Yeah.
It's imposed.
No, it's not imposed.
Yeah, it's pretty imposed because
Yeah.
like, it's a Laplacian vector. Goes from something
for the propagation. You're solving Laplacian, basically Laplacian equals 0 between.
Well, this, I mean, how you got the images doesn't, you know, different story, but I mean, if you have your score generative model, I'm doing for the unconditional stuff.
But the score is just for the epicardial, but this is not what you're observing. You're observing surface mapping.
Okay, so then you mean the likelihood function is very complicated.
Yeah, and it's really then it gets really imposed. Yeah,
No,
because
Bayesian problems are never imposed.
What?
You have a prior, I mean, that's what saves you, right?
It's like infinite dimension prior what's in
You already find that element.
Yeah.
Mentally speaking, we only find that element.
Yeah.
Otherwise, there is a
Yeah, but I mean, you know, we talk in finite dimensions, right?
yeah,
I mean, mentally.
yeah. Well,
But yeah, there are plenty of people. Actually, I did.
yeah, yeah,
People who are doing like classical.
yeah. I know, and it's and the,
inverse problems to solve this kind of problem.
yeah.
It's nice, but like you.
Yeah, this new. I think these new ideas we should try them in this guy.
Exactly, time dependent, inverse forms, you know, start from your guys from prior, you have your nice model, you generate it, and you train from the data, and then at the end of the time, you get an ideal function. So it's
Yeah, it's
just data.
I don't agree. No, it's like
And you should probably do variable because you only want to have one image anyway.
to
You don't
do
do it as a minimization problem. You don't need an example.
so. But the thing is that I think
For me, the neural network is the reduced model that actually is assimilated on the fly. So basically, it's more than basically. It's what you okay. For me, we did data assimilation using all the data at the same time to infer part of the model in the same time that's actually predicting something. So it's
because yeah.
comparison is unfair. Yeah.
You guys.